This question is titled, "Is this your first rodeo?" Isn't it interesting that nobody ever says, "This is my first rodeo"? In this question, we're going to talk about how we can enhance our predictive accuracy. And we're going to talk about extensions to simple linear regression, namely what ridge regression is and what lasso regression is. And when you read about these online, there's a lot of verbiage about these, but in truth, they are quite simple ideas. Remember, we have some linear function that we're trying to find these coefficients for, these beta coefficients. And we'll eliminate the intercept term. We'll assume that we're not trying to find that intercept. We'll assume that it's centered. We could say that the y value is some linear combination of all these x values, and we're looking for these betas. Another way we could phrase it is our guess is whatever the coefficients are, dot product against whatever our source data. In a linear regression, all we're looking to do is minimize a cost function, and the cost function we're looking to minimize is just the actual minus the guess squared, the sum squared difference between the actual values you see and the guesses that we have, which we could formulate in this fashion: the actual minus the coefficients dotted with the source squared. Ridge regression is just minimizing a cost function, and the cost function that it's minimizing is exactly the same cost function as linear regression with an additional term. A factor here, what's called the shrinkage or tuning parameter, multiplied times the squared sum of the coefficients. What's happening in ridge regression is you're not just minimizing the sum squared distance from the actual to the guessed, you're also adding a penalty factor where if the coefficients become very large, it'll raise that cost function. So it's going to try and find, when it's trying to minimize, it's going to try and find places where the coefficients are as small as possible. And you could think that shrinkage parameter, that tuning parameter, is just either accelerating or decelerating how much those coefficients are affecting this cost function. Because if you reduce that factor to, and I shouldn't say to 1, to 0, this is exactly the same as linear regression. Ridge regression with this alpha parameter, as they call it, of 0, this shrinkage parameter, is the same as linear regression. Lasso regression is merely minimizing a cost function, but I've changed the cost function very slightly. Instead of the sum squared difference, I'm looking at the, and I should write this like this, the absolute value, the sum magnitudes of the coefficients. So instead of looking at the sum squares of the coefficients, I'm looking at the absolute value of I'm looking at the sum magnitude of the coefficients. It's a very small, very slight difference between ridge regression and lasso regression. Let me show you this in practice, and then we'll talk about what it really means. Here, I have some data, and I have some coefficients, and I'm going to compute the training set that I'm going to look at. I'm going to perform a linear regression with my inputs and my outputs using scikit-learn, and these are the parameters it gives me. This is a fairly big model. It's got 10 parameters. I can show you that this is identical to just minimizing the cost function, which is just actual minus guesses and the sum square of them. And so when I minimize this just using scipy.optimize.minimize, I get the exact same values that my scikit-learn, because it's really all it's doing behind the scenes. Now notice, one of these parameters is very large. You could think that in a linear equation, if one of these is very large, it's going to start swamping the others. And that might be a problem because it might start to overfit. It might start to overwhelm the other parameters. And so if we wanted to penalize any one of these parameters from getting too large, we might use a ridge regression. And here is scikit-learn computing a ridge regression, and it gives me slightly different coefficients. And you can see it started to penalize this coefficient. If I bump up this alpha parameter, it'll penalize this coefficient even more. And the higher I bump up this alpha parameter, the more you'll see this coefficient starts to shrink. This is what that shrinkage parameter is doing. That's what ridge regression is doing. It's trying to shrink these coefficients, trying to find the best minimal cost function, taking into account the error and also the coefficients themselves. And this is exactly the same thing as if I just minimize and I add to my cost function that alpha parameter times the squared sum of the coefficients. Now, if I do a lasso regression using scikit-learn, I get yet another set of coefficients. And one interesting thing is it has zeroed out one of the coefficients that wasn't zeroed before. So you can see that one of the coefficients was identified in the simple linear regression as not really contributing to the model. That's how I set it up. Here, the lasso removed another parameter and said, you know what, we don't really need it. And it removed another parameter, actually removed a couple of parameters. This is a good thing because as part of our choice of parameters, if the lasso regression says, I found you a different fit that minimizes the size of the coefficients and also can zero out parameters, I found you a fit where I could tell you these parameters do not need to be considered. That could be very useful for simplifying our model because we don't need, great, we found a linear relationship with 50,000 variables. In practice, that's not going to be so useful. Now, we can compute this manually with scipy.optimize.minimize by just changing our cost function very slightly. Instead of the sum squared of the coefficients, we take the absolute value. But you see these do not actually tie out. This is because, at least for scikit-learn's, this is the formulation that's often used when people talk about lasso regression, but for scikit-learn's lasso regression, they add one other factor to the cost function, 1 divided by 2 times the number of samples. So if we just add in just this one little piece here, we can actually tie out more or less to scikit-learn's lasso regression. Why? Well, there's 2 things to discuss if we want to talk about ridge regression and lasso regression. First, the bias and variance trade-off. I'm sure you've all seen the discussion of accuracy versus precision, where they show you a dartboard and they show you accuracy is how close you got to the actual target, and precision is how close your values are clustered. Well, we can talk about this in terms of our fit. They can talk about this in terms of our regressions by talking about the bias and the variance. We can say that if we have a very high bias and a very low variance, we're actually underfitting. If we have a low bias and a high variance, we're overfitting our data. Well, if it's the case that we have highly correlated input data, what's called multicollinearity, then it may be the case that that is going to pump up our coefficients, and we're going to get something that's overfit to our data. We're going to see some parameters that don't really give us predictive power when you deploy them into the real world, because the relationships between the variables is going to create something with a coefficient that's going to start swamping out the effect of the things that are actually independent. What we could do is we could reduce the magnitude of the coefficients, and that would reduce the effect of this multicollinearity. That's what ridge regression is all about. It's about shrinking the coefficients to reduce this model complexity and the effect of this multicollinearity. Lasso regression is just another approach for doing it, and as a consequence of its cost function. And the mathematics behind this, you can see them visually, why it is the case that lasso is capable of reducing these to 0 and ridge isn't. But I won't go into that in too much depth. What I will say is you can see it in the example. Lasso not only shrinks the coefficients, but it also can facilitate feature selection by shrinking these coefficients all the way down to 0. Why do we care? It is the case that if we want to build a linear model, we want it to have as few parameters as possible, because it makes it easier for us to interpret that model. It makes it easier for us to work with that model. And we probably want it to be the case that we want to reduce the overbearing nature of any one of these parameters, because if there is some correlation there, we're going to get some spurious predictions from that. In general, ridge and lasso regressions can be thought of as simple extensions of simple linear regressions, your ordinary least squares that we've done 10 times already, with some additional penalty for those coefficients getting too large in order to deliver coefficients that are more likely to be predictive in the real world, where we are not over-biasing or over-minimizing that variance.